In my last video, we were looking at a very nice probability problem of a spider who's doing a random walk around a k-agon. Here, k just represents the number of sides. For example, k equals 5 is a pentagon shown here. Now, someone left a very nice comment on that video. Now, I wonder what e of t is. What is the expected value of t? And the t they're talking about is the random variable for the number of steps until the spider first gets back home. So they're going to walk left and right totally at random, flipping a coin every time, and just by chance at some point they end up back at their house where they started, and the question is, how long does that take on average? And that is the question I'm going to answer in this video. We're going to find a nice formula for the expected value of t. It's very simple and not too complicated. And then in the second half of the video, I'm going to answer Random Berfness's follow-up question, and what is v of t? What is the variance of t? Probably less easy, and they are right. So for e of t, in the first half, I have a nice animated proof, and for the variance of t, we're going to have to crack into some more advanced methods using something called the Exponential Martingale Method, which is a really great method for calculating this kind of thing in probability. So let's start with the first question first. What is the average number of steps until the spider gets back to their house? And you can write this as e of t. And the interesting thing to see is, how does this depend on the number of sides of the shape? And you can imagine as k increases, it gets harder and harder for the spider to go all the way around, right? When k equals 5, he just needs 5 steps to do a full loop around this pentagon. But when k equals 100, he needs to go a lot further to go all the way around. So how does it depend on k? And the very beautiful answer is that it is exactly k. So the more sides you have on the shape, the longer it takes the spider to go around, and the amount of steps it takes him, on average, is exactly k, the number of sides of the shape. This is a very surprising result. Like, you might think that, oh, when k is very large, he'll just go out and back, and it won't take him much longer. But it turns out if you double the number of sides, you also double how long it takes him to get back on average. Very interesting and maybe counterintuitive result. So one way you could calculate this is you could try to calculate the probability he gets back in 2 steps, the probability he gets back in 3 steps, and try to add them all up. Now, this would lead to a big infinite sum with these probabilities. And that is actually going to be quite hard. So for example, in my last video, we actually did calculate these probabilities when k equals 5, and it leads to this infinite sum with Fibonacci numbers. And this is a real doozy of an infinite sum. It turns out this infinite sum of Fibonacci numbers does work out to exactly 5, but proving it is pretty tough. So we're going to skip over all of that, and we're going to do it a totally different way that lets you calculate these expected values just on their own. And it's a very nice trick that works on a lot of situations like this. Let's see what the trick is that lets us avoid doing any of this infinite sum stuff. So the first thing we're going to do is unfold this shape and think of it as a straight line from left to right. So the spider, instead of moving clockwise and counterclockwise around the shape, he's going to be just going left and right on this straight line segment. The house on the left represents where he started, and the house on the right represents where he would get to if he went all the way around the shape. And on this straight line segment, we're going to label where the spider is by x. And we're going to say he's at position x when he's x steps away from this little house on the left where he started. And now this is the key idea, I think, of the entire method. Is we're not just going to try to calculate how long does it take for Mr. Spider to get home from where he started. We're going to try to calculate how long it takes him to get home from any position x. So we're going to make this function called f of x. And f of x is going to represent how long it takes him to get home when he starts at position x. So when he's 3 steps away, that would be f of 3. What we want to calculate is actually related to f of 1, because his first step is always 1 step away. And you might say, look, you just made the problem way harder. We had to calculate one single number before, and now you're telling me we're going to calculate a whole function? You're crazy. You just made it way harder. But the nice thing is that this function f depends on itself. So we can come up with a nice equation for f and then solve it in a way that if we were just trying to calculate one single value of f, it would be much harder. And what equation are we going to get? Well, it's a very simple equation. The first part of the equation says f of x equals 1/2 f of x plus 1 plus 1/2 f of x minus 1. And this represents the fact that the spider can either step left or right. So starting at position x, half the time he will step to the left and end up at position x minus 1, and half the time he will take a step to the right and end up at position x plus 1. And that is what these x plus 1s and x minus 1s represent over here. It just represents how the spider moves, and with these 1/2s representing the probabilities. Now, there is one super important term I left out of this equation that absolutely needs to be there, and that is a plus 1. That plus 1 represents the fact that when he moves left or right, he is taking 1 step, right? So basically this equation, you can read it off as saying, okay, he's starting at position x. He's going to take 1 step, and he's going to either end up at x minus 1 or x plus 1. So how long it takes him starting from x will be how long it takes him starting at wherever he ended up, plus the 1 step he took in that turn. So this is the equation that f satisfies. If we can find a function f that solves this, we will know what this is, and we'll get what we're looking for. There's one other thing we want our function f to satisfy. The function f has to have the right values at the endpoints, and those are f of 0 equals 0. So if he starts at the house, then he's done. It takes him 0 time to get to the house, starting at the house. And f of k is also 0. So if he starts at the other side, representing going around the shape, that will also take him 0 extra steps to get back home. These three ingredients, the two values at the endpoints and this equation that we found for f, together, if we can solve it, we will know the answer. Let's try to solve for this function f, and I'm going to rearrange it a little bit and write it like this. The ICs stand for initial conditions, and DE, you might think, stands for differential equations. Here, it's not a differential equation, it is a difference equation. And to make it look like a difference equation, I'm just going to rearrange it a little bit. And I've written all the parts with the f on the left-hand side as a difference. And so this is saying that the difference of these f values, f minus its value at x plus 1 minus its value at x minus 1, that difference equals 1. So if we can solve this difference equation, what function f satisfies this difference with those initial conditions, we will have our answer. And this difference equation at first glance maybe looks totally crazy, but it has a nice intuition, so let me draw it out for you. Here's some function f. Pretend f is some kind of curve like this. If you draw the value of f of x, the value of f of x minus 1 and f of x plus 1, those are a little bit to the left and a little bit to the right of the function f. Now, we are not doing f of x minus 1 or f of x plus 1. We're doing 1/2 of f of x plus 1 plus 1/2 f of x minus 1. And that can be visually represented as the midpoint of the line connecting these 2 points. So what does our differential equation say? It says that if you take the value of f and you subtract off the midpoint of this like plus minus thing, the little red dot that I've drawn over there, then that difference, that is the thing that is always equal to 1. So that difference has to be 1, and it has to do that for every value of x. So as you kind of shift along for different x values, that difference is always 1. F is always a little bit above where you find this midpoint. The function that satisfies this is always going to be concave down. It's always going to be curved sort of downwards. And in some sense, this is saying the amount of concavity is constant. It's always concave down by the same amount. And so you might guess, okay, what could the function f be? It might be our favorite function. Let's do a guess and check. F of x equals minus x squared. And let's check and see if this solves our equation. So let's do a little bit of algebra. If we plug in minus x squared into our equation, we see we're comparing minus x squared to x plus 1 squared and x minus 1 squared. And if you expand these things out, you see by the rules for expanding squares that very nice things happen. So we have some nice cancellation here. The x squareds all cancel out. We have a minus x squared from the f, and we have a 1/2 x squared and another 1/2 x squareds from the other two f of x plus 1s and f of x minus 1s. Those perfectly cancel away. The next miracle is that not only do the x squared cancel, but the x's also cancel. So the x from the plus 1 cancels with the x from the x minus 1. Those perfectly go away. And what is left over is 2 copies of a half. A half plus a half. Those combine together to give us the 1 that we want. And indeed, minus x squared satisfies our difference equation. Yay, we did it. All right, what about the initial conditions? Let's plug in minus x squared into our initial conditions and see if they are satisfied. Is f of 0 equal to 0? Well, yeah, you plug it in. 0 squared is 0. Unfortunately, there's a problem here. When you plug in k, f of k is not equal to 0. It's minus k squared. That is not what we want. So we have a solution to our difference equation, and we have one out of our 2 initial conditions, but not the other one. Fortunately for us, this equation is what is called a linear equation. So if we can find a different solution and add it on, we can try to, rescue that other initial condition. And in this case, the thing to add on is a perfectly straight line. So if you add on the term k times x will also satisfy the difference equation. And let's see that. So if you do k times x, and then you do k times x plus 1 and k times x minus 1, everything perfectly cancels out. So the x's go away, and then you have plus 1 and minus 1. Those perfectly cancel out. So adding on k times x, we will still satisfy the original difference equation. Very nice. And to check the initial conditions, you can do a nice factoring to write it as x times k minus x. And you'll see that at 0, it's still 0. And now at k, it is also 0. So this equation, x times k minus x, by doing guess and check and sort of fixing up our answer, we were able to solve the difference equation with both initial conditions. And now that we have the solution by guess and check, we can go back to our original picture, and we can actually see that it has a nice interpretation for Mr. Spider. So x is how far away he was from the left side, and k minus x is how far away he is from the right side. So this is saying that f of x is the product of how far away he is from the left with how far away he is on the right. And this makes perfect sense. We're talking about how long it takes him to get home. It makes sense that it would take him more time to get home from the middle than when he's close to either end. And so this product is sort of quantifying exactly how much time it takes him to get home. Wonderful. Let's make sure we go back and answer the original question now. How long does it take Mr. Spider to get home starting from the house? So starting from home, in Mr. Spider's first step, he's going to definitely move to x equals 1. And so how long it takes him is how long it takes him starting from x equals 1 plus the 1 first step moving from the house to x equals 1. And we know what that is now. That's the function f of 1. So we plug in f of 1, and we see that's 1 times k minus 1 plus 1. Altogether, that is k. And that answers the question that random Barfus had. Now let's try the follow-up question. What about the variance? And this one is indeed a lot harder. For just the average amount, the expected value of t, we were able to do it by guess and check essentially. But for the variance of t, we're going to do a more systematic approach that you can always do for any kind of random process like this. To do this, we're going to need the power of algebra and equation solving. And the best place to build your math muscles for this kind of task is the sponsor of today's video, Brilliant.org. No matter what technical topic you might want to practice, Brilliant's got a course for you. They've got great classical math courses like algebra and calculus, as well as courses about computers like programming and dealing with data. If you're looking to improve your algebra skills, Brilliant's visual algebra course is the perfect tool. By showing you visually what's going on with these equations, you'll build an intuitive sense behind the algebra. And when it comes to solving equations, Brilliant's got a course for that too. You can see what the algebra steps actually mean and how they come together to solve an equation. Brilliant brings it all to life with their many practice problems. This interactive and visual approach to learning is proven to be much more effective than just lectures alone. To try everything that Brilliant has to offer free for a full 30 days, scan the QR code on screen here or click the link in the description below. You'll also get 20% off an annual premium subscription. Thanks to Brilliant for sponsoring this video. So in the second half of the video, I'm going to answer the question, what is the variance of t? And it's going to be a little bit more systematic than the guess and check method we used for the expected value. And I have some ingredients on here that are going to help us out. The first most important ingredient is what I call the golden equation. And it is a equation just like we had in the expected value, but this time the thing to notice, it is a function of two variables. So before we had an f of x, now we have an f of xt. And again, it is satisfying this equation with the x plus 1 and the x minus 1, so very similar to what we had before, but now there is a time parameter that is going up by 1. So we'll see where this equation comes from and what exactly it means. It is some kind of generalization of what we did before by adding this t parameter in, and that gives you a lot more flexibility to solve more complicated problems. And I also have 4 solutions to this equation, what I call my 4 golden eggs that solve my golden equation. I call them A, B, C, and D. And they are all solutions to this equation. So if you plug them in, you will find they work. But the amazing thing is I didn't just get them by guess and check. I actually got them from my golden goose. And my golden goose is something called the Exponential Martingale. We'll see what this is. And it allowed me to easily generate these 4 solutions. And then I used the 4 solutions to get what I wanted. And this is a very general technique. You can always calculate this exponential martingale, and then you can squeeze information out of it, if you know how to solve all sorts of things. So to start with, we're going to interpret this equation in terms of probability. And in fact, that is where the equation comes from. So you never actually need to write down this full equation. You just need to write down what it means in terms of expected values. So the easiest way to make sense of this is to give some notation to the location of the spider. So I'm going to call capital X sub t. That will be a random variable, which is the location of the spider at time t. So this is a random variable for any time t, and as time t changes, you can kind of think of it as a random process in time. And you can take this random process, if you feed it through a function, you will get some other random process. So f of x t, comma t, this is some other random process in time. And we would like to find a function f so that when you do f of xt, comma t, on average, it doesn't go up or down. On average, it stays exactly flat. And that is exactly what the equation we want says. So let's write it out. In expected values, you would write it like this. You would say the expected value of, I'm going to do time 1, at time 1, x1, comma 1, that is equal to whatever it is at time 0, f of x0, comma 0. And that is also equal to what it is on average at time 2, and so on and so on. So as time changes, the value of x is changing, time is going up by 1, but no matter what you do, no matter how far into the future you go, you can do this as many steps as you want. On average, f of xt, comma t is neither going up nor down. And this is called the Martingale equation. And when f satisfies it, then the f of xt, comma t is called a martingale. And now if you were going to write down what this is, the expected value of f of x, comma t, you would get exactly this equation. And that's because we know from our random walk that when you take 1 step forward in time, t goes up by 1. So moving forward in time by 1 step, t goes up by 1. And also the x value either goes down by 1 or up by 1, each with probability 1/2. So this equation over here is exactly saying that f satisfies what is called this Martingale equation of, on average, it doesn't go up or down. Now, why is this equation useful? Why would you want this Martingale equation? Well, the reason is, if it's not going up or down on average, you can even stop it at some random time in the future, and in particular, we're going to stop it at time capital T. So this is something called the optional stopping time theorem. And it says that if you have this Martingale, not only is it true at any individual time, it's true at a random time too. Okay, there's some terms and conditions. I'm going to skip the checking the terms and conditions. You just have to believe me that they hold. And what it says is f of x0, 0, whatever the value of the Martingale is at time 0, that will also be the average of the Martingale at some later time, in particular at the time when Mr. Spider finds his way back to the house. So, and this really is the equation. This is the key equation we're going to use over and over again. And I already have 4 solutions f that will work. So if I take the 4 solutions and I use this equation, we will extract out the information. At the end of the video, I'm going to show you how you get the 4 solutions. But for now, let's take these 4 equations, and we know they all satisfy this Martingale equation. Let's plug them in to the optional stopping time theorem and see what we get. If we use the function a of xt equals x, let's see what we get. So plugging in this function into our optional stopping time theorem in that big red box, the left-hand side, it just says x0, and the right-hand side says the expected value of x capital T. Now, x capital T, that is the location of the spider at the moment t where he exited that interval. So remember, our spider is walking on this range, and there's 2 places he can exit. He's got a little version of his house here at 0. So this is at x equals 0, and he's got another copy of the house at x equals k. He starts at x0 equals 1, and he's going to move around. Sometimes he will exit on the left at x equals 0, and sometimes he will exit on the right at x equals k. So if we plug this in now, on the left-hand side, x0 is always 1. That's very nice. And on the right-hand side, the expected value of xt is a combination of these 2 probabilities of exiting on the left and exiting on the right. So it's something times the probability we exit on left plus something times the probability we exit on right. And what are the 2 somethings? Well, when we exit on the left, what is the value of xt? It is 0. And when we exit on the right, what is the value of xt? It is k. So it's 0 times the probability we exit on the left plus k times the probability we exit on the right. This just becomes 1 equals k times the probability that Mr. Spider exits on the right, that he exits at the position x equals k. And this already tells us something we didn't know before, which is that the probability that the spider exits on the right is 1 over k. So this is our cool first fact that we've learned from this Martingale equation that we didn't know before. So before we were saying sometimes he exits on the left and sometimes he exits on the right, and now we know exactly what the probabilities are. So most of the time, k minus 1 out of k times he will exit on the left, and 1 out of k times he will make it all the way to the other side. We have discovered this fact by using that solution a of xt. Okay, what do we get if we use the function b of xt? So this is kind of our part b of xt, and it's the function x squared minus t. So let's plug into our optional stopping time theorem, this thing in the big red box, and see what we get. And what we get on the left-hand side is x0 squared minus 0. And on the right-hand side, we have the expected value of capital xt squared minus t. Okay, this is very interesting. The left-hand side, again, simplifies very nicely. That is equal to 1. What is going on the right-hand side? We can write it as a combination of 2 things. We can say the expected value of xt squared minus the expected value of t, so splitting that up into 2. And just like before, the expected value of xt squared, where there's 2 possibilities for x sub capital T. Either we exited on the left or we exited on the right. Those are the only 2 things that can happen. So this is going to be 0 squared times the probability we exit on the left, plus k squared times the probability we exit on the right. All right, all of that minus the expected value of t. So this is a very nice equation, and fortunately, we have already solved with our previous function. We've solved for exiting on the right. We know that that is 1 over k. So if we plug that in, on the left-hand side, we have 1, and on the right-hand side, we have 0 plus k squared times 1 over k minus the expected value of t. This is a beautiful equation, and it tells you that the expected value of t, after some rearranging, is just simply k minus 1. Very nice. This is actually what we did in the first half of the video. And in fact, this Martingale, x squared minus t, the fact that b of xt satisfies our equation, actually, if you plug it in, because the dependence on t is just t, literally is the equation from the first half of the video. So somehow in parts A and B, we've kind of redone what we did in the first half of the video, but with no guess and check. I guess you still need to know where do these equations come from, a of xt and b of xt, and I will show you where that comes from the golden goose at the end of the video. All right, but let's keep crunching along. What do we get from part C? See, this is yet another function, and it's a very funny looking function now. It's c of xt equals x cubed minus 3xt. And if you take this and you plug it into our optional stopping time theorem in the big red box, what do we get? Well, on the left-hand side, we are going to have x0 cubed minus 3 times x0 times 0, and that is going to be equal to the x capital T cubed minus 3xt times t. The left-hand side simplifies again. It's just 1, like it always has been. On the right-hand side, what is going on? We have the expected value of xt cubed. We know how to do that one because we've done it a few times now. It's 0 cubed times the probability we exit on the left, plus k cubed times the probability we exit on the right. The 3xt, that one is a little bit more interesting because it depends on how the random variable t depends on our location of exit. So in fact, what you're going to get is 3 times 0 times the expected value of t, but only on the event that we exit on the left. So I'm using this 1 here as an indicator function to mean that we exited on the left. We also have the other situation where we exit on the right. It's 3 times k times t times the event that we exit on the right. And just like before, these values, k is coming from the xt. When we exit on the right, xt equals k, and that's why we get this factor over here. And now we know this probability that we exit on the right, and it's going to let us solve for some piece of information that will be useful to us. Let's plug everything in and simplify. So you get 1 on the left-hand side, k cubed times the probability you exit on the right. Well, we said that was 1 over k from part A, and we have some zeros. We also have minus 3 times k times this funny thing, t times the indicator that you exit on the right. And if we rearrange, we can solve now. So the amount of time it takes us when we exit on the right on that event is k squared minus 1 over 3k. This is like approximately a third of k. And so of the total amount of time that we found in part B, we found that on average it takes k minus 1 steps for the spider to exit. Well, a third of that is coming from the situations where he actually does the rare event of moving all the way over to the right-hand side. So those situations, even though they're rare, they take a really long time. And so they still have a macroscopic sort of contribution to the expected value. Okay, and last but not least, we're going to use the martingale in part D, the D martingale, and that is this equation over here. This is the moment where I will reveal that there is actually a very important typo. This should be a plus. This should be a plus. So I actually recorded some of this, and it turned out it was wrong, and now we know why. And once again, you might be totally stumped on where do these terms come from, but I will explain how the golden goose will give us all these A, B, C, Ds in a minute. So let's plug in to that equation. We're going to use the function d of xt is equal to x to the 4 minus 6t x squared plus 2t plus 3t squared. And if we plug into our optional stopping time equation, on the left-hand side, plugging in x0, comma 0, you get simply 1. So the left-hand side is 1. And on the right-hand side, we have, as usual, the expected value of this thing at that final time, capital T, 6t xt to squared plus 2t plus 3t squared. All right, very nice. And once again, we can simplify the right-hand side. The first 3 terms are all things we know. So we're going to be able to calculate and know exactly what the first 3 things are from our work in parts A, B, C. And the last thing, that is what we want to know. It's the expected value of t squared. And because we know everything except that, we're going to be able to pull that out. The first little bit simplifies it nicely, just like we've been doing before. We have a 0 to the power 4 times the probability we exit on the left, plus we have a k to the 4 times the probability we exit on the right. The next part is this weird combination of x and t, just like we had before. And once again, it depends on the expected value of t, both when it exits on the left and on the right. And in this case, it's going to be 6 times 0 squared times this expected value of t when we exit on the left. And once again, when we exit on the left, xt equals 0, and that is why we get a 0 squared. We also have the same contribution when we exit on the right, and that's going to give a k squared, because when we exit on the right, xt is k. Okay, so those are the first 2 terms. The next term is 2 times the expected value of t. Fortunately, we calculated that way back in part B. And last but not least, we have what we actually want to know, the expected value of t squared. So we know all of these ingredients except for the expected value of t squared, and so we can rearrange and solve. So plugging in what we know, we're going to have a k to the 4 times 1 over k, because this probability was 1 over k. These two terms are all 0, those go away. And we're going to have over here a 6k squared, and then this is where we're going to plug in the thing we calculated from part C, the k squared minus 1 over 3. And that was exactly what we calculated before that we're using now, which is that this thing is k squared minus 1 over 3k. Plugging that in. The expected value of t we also know. All of this altogether has to be equal to 1. This is the optional stopping time theorem for that function d of xt. And now we simply have to rearrange. The expected value of t squared is equal to... So after all that work, we have some polynomial equation for the expected value of t squared. And finally, we can find the variance of t, which is what we wanted, is the expected value of t squared minus the expected value of t all squared. And it's going to be this polynomial. So there you go, that's the variance. So if you simplify this, you'll find a very surprising thing, that this actually equals, after some simplifying, equals 1/3, and a very nice formula, k times k minus 1 times k minus 2. This is extremely nice. There must be some simpler way to get this variance. So instead of getting this crazy thing for the expected value of t squared, and then subtracting off, and then doing some massive algebra to simplify this, maybe there's some faster way to get directly to this final answer. I will leave that as a challenge to the interested viewers. So there you go, we've calculated the variance of t using these functions a, b, c, d along the way. And every single time you use a function, you gain a little bit more through the optional stopping time theorem here in the red box. You gain a little bit more knowledge about what's going on. And by stacking it up all together, you eventually can crunch out anything that you would like to know. Last but not least, the thing I have promised many times now is, where did these solutions come from? Where did I find the solutions for A, B, C, and D? I got them from this equation right here, which I call the golden goose that laid those 4 golden eggs. This is the exponential martingale. And what it is it's a solution to the Martingale equation that depends on this parameter alpha. And by varying alpha, we can squeeze out these A, B, C, D things. But what is this solution anyway? Let me tell you what it is. So the only probability calculation I had to do to figure out those functions A, B, C, and D is to write the random walk. I wrote capital XT, I wrote it as a sum. So there's a delta x1 plus a delta x2 plus ... where these delta x's are fair coin flips. So each delta x is either +1 with probability 1/2, or it's -1 with probability 1/2. So by writing the position of the spider as the sum of these random variables, I can analyze this coin flip random variable, these delta x's, individually. And the thing that I calculated was the expected value of e to the alpha times delta x. And this is a very nice calculation because we know it's +1 or -1 each half the time. So this is half the time it's e to the plus alpha, and half the time it's e to the minus alpha. And in fact, this formula has a name. This is the hyperbolic cosine, or some people like to call it the cosh of alpha. So by doing this calculation and figuring out the expected value of the little increments, the delta x's, when you exponentiate them on average, that is what let me make this martingale, my golden goose martingale, that depended on a parameter alpha. And specifically what I said is, look, if every individual increment on average is the hyperbolic cosine of alpha, then if I wanted to do, I can write e to the alpha xt, that will be e to the alpha delta x1 plus ... all the way up to delta xt. And when you add things together in the exponent, that is a multiplying the things on the outside. So this is e to the alpha delta x1 times e to the alpha delta x2 times ... times e to the alpha delta xt. And when you take the expected value now, so if I do the expected value of both sides here, I do the expected value on the left-hand side, it's very simple. And on the right-hand side, because each of these coin flips are independent, I can split the expected values like this. And I calculated each one of these. Each one of these is a hyperbolic cosine. I have t of them in a row. This is equal to the hyperbolic cosine of alpha all to the power t. So what this says is on average, if you do the expected value of e to the alpha x, on average, it is equal to the hyperbolic cosine all to the power t. And therefore, with a little bit more thinking, therefore, if I do e to the alpha xt and I divide it by the hyperbolic cosine of alpha to the power t, the average of this is always 1. So if I take the average value of this whole thing, this is always equal to 1. And you have to do maybe a little bit more thinking with these increments, but this is showing that therefore, the function f of xt, which depends on alpha, which is the function e to the alpha x divided by the hyperbolic cosine all to the power t, this always satisfies the Martingale equation. And so this very simple method, this thing is called the exponential martingale. And anytime you have something made out of little increments that are added together, you can always calculate this exponential martingale by the method I sort of just showed, and it will always be a solution. Now, it's not a very useful solution because it depends on alpha, but actually from this solution, from this golden goose, you can get those 4 golden eggs, A, B, C, D, that we use to calculate the variance of t. And the way you do it is you use derivatives. So actually the function a of xt is equal to the derivative with respect to alpha of f alpha of xt when you plug in alpha equals 0. So you take one derivative, then you plug in alpha equals 0, that will give you a of xt. And b of xt, maybe you can guess what is going to happen. So you do 2 derivatives, d squared d alpha squared of f alpha of xt, and then you plug in alpha equals 0, that will give you b of xt, and so on and so on. C and d are also the 3rd and the 4th derivative. So c is the 3rd derivative, and d of xt is the 4th derivative. So because the function, the exponential martingale, is this whole family of solutions, you can combine the solutions in all sorts of ways, and one way you can do that is the derivatives, and these give very nice, helpful things. Now, of course, you could do this all by hand, but nowadays, it's faster to do it on a computer. So that's what I did. Here is a quick computer program that did all these derivatives. So here is a quick little Python program that did those derivatives of the golden goose, f alpha, and calculated a, b, c, d for me. So I did it in the SymPy package, and I made these parameters a, x, and t, and I said those are some symbols. A here stands for alpha. Maybe I should have called it alpha, since you're not limited to letters on a computer, but you have alpha, x, and t. So those are symbols. And then I made the function f. This is the function. It's e to the alpha x divided by the hyperbolic cosine of alpha all to the power t, and that's f. And then I just did 5 derivatives. So I did the derivative of with respect to alpha n times, where n is in a loop here going from 1 to 5 times. And then I evaluated it at 0 by doing dot subs alpha equals 0, and then I simplified it a bit. And you get exactly those functions a, b, c, d. So if you do 0 derivatives, you just get 1. That's not very interesting. 1 derivative gives you a of x, which was x. 2 derivatives gives you b of x, which was x squared minus t. 3 derivatives gives you x cubed minus 3tx. And 4 derivatives finally gives you this thing, that final thing that let us calculate the variance.